Next speaker, Ben. Let's see, he's lead architect for one of the first and highest volume Elixir customers, Bleacher Report. Author of Adopting Elixir with Jose and Bruce here. And good developer, pretty decent. Better guy. And perhaps the only person in the building who's gotten less sleep than the City Elixir team. Everybody give it up for Ben.
Thanks for the introduction. I've been using Elixir for a long time in production, about 5 years now, I think. And as I've moved away from writing code on a daily basis, and as our systems have become more complex, my job right now is more about verification and figuring out how things are going to work. Like I review a lot of tech specs. I work with people on different teams. They bring architectural ideas, and we work on them, and so forth. And this works pretty well, but it also makes me a bit nervous because how sure can we be, especially as our system gets more complex, that we're taking care of all the things that we need to take care of? And really, you can't. It gets very difficult. So this is where TLA Plus comes in. And this isn't a talk about Elixir, but Elixir is billed as concurrent, fault tolerant, highly available, all these things that we know that Elixir is good for. And TLA Plus will verify your systems. So this is what we're going to talk about. It's it's going to be a quick talk, so I'm not going to get too deep into things. And I also understand that there aren't going to be that many people that are going to take run with TLA Plus for a number of reasons. One, it's not a very easy thing to use, and two, it can be hard to find justification for it. So we're going to talk about what it is, an overview of it is. We're going to have a simple example, and then practical application. And practical application in this context means industry use, as well as some lessons that you can take away that if you're never going to use this application, maybe they can influence how you design and build your systems. So what is TLA Plus? TLA Plus is a class of programs that deal with formal methods for verifying things. Leslie Lamport, he's a seminal figure in distributed systems. He probably has the sort of ubiquitous quote about distributed systems, which is roughly a distributed system is one in which a computer you don't know exists causes your own to fail. Which says quite a lot about distributed systems in a very short amount of time. And so Lamport invented TLA Plus in 1994, and this is a sort of a culmination of about 2 decades of work on formal methods. And just to give you, if you've never heard the name Leslie Lamport before, here's a short sample of some of his important papers proving the correctness of multiprocess programs, time clocks, and the ordering of events in a distributed system. What good is temporal logic? And the TLA in TLA means temporal logic of actions. So there's some good to it. Byzantine generals problem, the part-time parliament, colloquially known as Paxos, which is also very difficult. It's sort of a Greek allegory. So he wrote another paper called Paxos Made Simple, and the abstract is a bit tongue-in-cheek in the sense that Paxos algorithm, when presented in plain English, is very simple. So of course, simple for one person is not easy for another. They're not necessarily the same thing. In this case, they certainly aren't, because Lamport's idea of simple might be quite different from one of our own. But this idea of simple is something very important, and we'll sort of keep this idea of simplicity throughout the rest of the talk. So TLA Plus isn't a programming language per se. It uses math and mathematical modeling to give very precise definitions of how your system, or what your system is going to do, rather than how it does it. And even though it uses very precise language with mathematics, it's not designed for mathematicians and for researchers. It's designed to be used in industry. So it's a practical application of these very complex mathematical ideas. And if you're really interested in the underpinnings of that math, there's a talk by Ron Pressler called The Practice and Theory of TLA Plus, which goes into it very deeply. And it's a great talk, and he's also a great writer. So, and another thing, natural language is a funny thing, right? Based on our backgrounds, based on what our first language might be, when we communicate with each other, we talk in imprecise terms. So my wife's first language is not English, and so she has some she has her own way of attaching words in her native language to English words. And so we've had to sort of develop, over the years that we've been married and been together, we've had to develop this sort of common language. So we'll say a word in English, And it'll mean one thing to me, but because of her Japanese primary language, it'll mean something slightly different to her. So we had to kind of come up with this language, with this common language between us. And this isn't like, she's basically a native speaker at this point. So this is the idea that these nuances that exist are quite difficult to capture, especially when you're talking about something as difficult as a concurrent and distributed system. And so I bring this up because Lamport coined the term Whorfian syndrome, which is after the Sapir-Whorf hypothesis, which essentially says that the language we use shapes our thought. And this is something that, especially when we talk in computer science terms or development terms, these terms are quite imprecise as well. We say things and we don't exactly know what these words mean to you. So we have these abstractions that mean slightly different things. With math, there's one meaning, right? You can, no matter what you do, it's the same thing. And so this makes it very, this is really the only way, I guess, to reason about these kind of things. And he also calls TLA plus a layer above code. And you can liken it to a blueprint of a house, right? The house itself, the construction of the house is the code, and the blueprint is the layer of the code. And this focus on what the program should do rather than on how it should do it. In just the same way, like if you have a blueprint, you can design something in any number of ways. The blueprint just tells you how it should happen. And this can be a powerful tool because it's also language agnostic. I mean, if it's a layer above code, it doesn't matter what code you're writing in, right? So for instance, say you make a TLA plus spec, and you're benchmarking two different languages, or you're prototyping a piece of a system, and you want to compare two different languages. You can use TLA plus to ensure that the functionality is the same, and then write the code in whatever languages you want. And further from that, like this doesn't prevent code level bugs. I mean, this should be clear. If it's a level above the code, it's not going to prevent any code level bugs. So this doesn't circumvent any need for tests, property tests, et cetera. Again, it's how things work, or what they should do rather than how they work. So now we're going to show an overview of TLA plus. This is a pretty quick overview. And this is the book that I used to learn TLA plus, or continue to use to learn TLA plus. It's by Hillel Wayne. There are other resources to use. The TLA Plus website has a good resource. Leslie Lamport has a YouTube series with a nice bucolic background. But this, I'm nothing if not pragmatic. And while the theory is important to verify that these things are true, I want to see if this is something that we could actually use in my day-to-day job. Is this something? And this is a way to get started with it. And Hillel Wayne does a lot with formal methods and verification. So if you're interested in that kind of stuff, he's a great person to follow. So at its core, TLA plus consists of two things: a spec, specification, and a model checker. And the spec is essentially the blueprint. So this is the simplest sort of shell of a TLA plus program. You have a module name, and you can extend things, which is essentially importing different bits. And you have an algorithm name, and then begin is where the action happens. In this case, skip means just do nothing, return. And then it ends with at least four equal signs. So, nice and concise, but this actually isn't even TLA plus. This is a language called Pascal, because TLA plus it transpiles to TLA plus, and there's a prolix syntax and a T syntax. And if you transpile this is what you get. This is the same thing, and it's quite a lot. So if you've taken formal logic classes, you can probably recognize some of these things. And the nice thing about having, assuming that everyone here is a programmer and has done some programming work, a lot of these sort of logic that you'll need to understand, you sort of implicitly understand having used computers, or rather having programmed things with various truth tables for and, or, not or, sort of these kind of things. And then you have the model checker, and this is where this is the verification that happens. And here, this is what it looks like. I just want to point out a few things. Like in the next section, we'll go over this in more detail. But the temporal formula, the spec, that's what runs your spec. You can check for deadlocks. You can have invariants, which are things that happen at every single state. And as you can imagine, as your specs get more complex, the possible state space can get into the millions and so on range. So there's no way you can reasonably check this without using a program like TLA+. And then on the bottom, this property of temporal formulas, this termination property is something that we'll look at as well, which can give you some interesting things to think about. And this is what happens when it runs. I mean, this is a simple one. You can see that there are 8 states, 7 distinct, and everything passed. And so if that's sort of all you need to know about, there are other things about TLA Plus, but just the fact that there's a spec and a model checker, and the model checker will validate the spec. So let's go into a simple example. We can do producer-consumer. Brett sort of mentioned that I was tired. My wife and I had a baby a couple months ago, so I guess this producer-consumer model has been in my mind a lot. I've been on paternity, and I just got back to work, so it's a bit unfair to say producer-consumer. It's more like producer-consumer-consumer, but you know. And there's a lot of other stuff in there. So, but this has been on my mind. So this is sort of what it looks like, and I'll walk through this bit by bit. But you can see from line, basically the TLA plus, or the PlusCal starts at line 5 and ends at line 27. And one thing I neglected to mention is that the parentheses, asterisk, opening, closing, those are comments. So the reason this is commented is so that when you run the program, TLA Plus doesn't try to parse it. So you can see here at the begin translation and all of that, that's the actual program that is run. So let's look by this bit by bit. Again, like you have a module name, this matches the file, and you can bring in, import different modules, and integers, TLC, et cetera. And here's where the interesting stuff begins. So basically what this is saying is you're declaring variables. You have a set of produce from 0 to 5. You have a set 115 for demand. And then this producer and consumer variables, they're roughly akin to structs. I'm not a mathematician, so I'm going to speak fairly imprecisely about these kind of things. But it'll probably be more useful to have some things to relate to. So essentially what this is saying is that the producer has a key, produce, and if the value is produce, which could be between 0 and 5, and demand has a value between 1 and 15. And then here, these are what we call invariants, and this is how you write them in PlusCal. And so essentially this is saying no negative production, because it wouldn't make sense for a producer to produce negatively, or what do I mean? And vice versa, you don't want to have a negative consumption. And these, you could name these a bit more accurately, because you can see that produce can be 0, whereas consumption has to be greater than 0. So maybe the invariant names could be a little bit better. And then here you see this is what's translated into TLA plus. And so this is fine, right? This is kind of interesting. We have some things set up, but this is where TLA plus starts to shine. You have a process. And this is how you can enable concurrency. So you have a process, you name it, and then here we have 2 processes running. And then here we have a begin block and the end block, their end algorithm. And these 2 things like produce and consume, these are labels, and the labels represent steps. So the more labels that you have, the more variable states that you can have, the greater the state space, the greater confidence you can have in your model. And so this is really simple. And what happens is that every time it runs these concurrently. So these can happen in any different, in any different order at any amount of time between the number of possible state space. So when you run it, it fails, and you can see that there are 272 distinct states over here. And so you can get to, even though it's a very simple model, it would be really difficult to check 272 cases manually, or even with testing. And the nice thing is you have an error trace here on the bottom right, and it gives you the initial predicate, and you can see you have state number 1, number 2, and number 3, and it can show you where things fell. So you see that it's running the labels that are produced, and it's giving the values of consumer and producer. And you can see on line there under at the bottom where consume is 0. So that invalidates our invariant, which says that demand consumption should never be 0. And so, how would you do this, right? You could put a check on this, like if you can't guarantee the order of things that are run, how would you take care of this? So this is what you would do, right? since we want to be able to have these things, we want to put some constraints around what can happen, right? So we want to make sure that if the consumer is trying to request more than the producer can produce, then the producer should produce the amount that's demanded. And then, the variable names might be more accurately termed here, but this essentially will check to make sure that these conditions are met, and then it'll run it. And then I should also mention that the first time you assign a variable, you use an equal sign, and the next time, any other time after that, you use this colon equal sign. So then if we run it again, we see that it passes. This is great. And now you can see also that we have 570 states found and 390 distinct states. So again, these small changes can have vast impact on your software. And this is a really simple example. So now let's play with a little bit more on this. So as I mentioned, the T in TLA stands for temporal. This assumes that things happen. And this assumes that things happen until they can no longer happen. So all the states are run, right? Like there's nothing else that it can do. The program has exhausted what it can do. So here you have the invariants that are checked on each state. And now you can also have this thing called termination. And so what termination does is what you might imply. It means that things stop. Like they don't have to run. So now if we run it again, we can see that you have many more states, almost I think it's quadruple what we had before in about 1,400 distinct states. And then on the bottom, it failed because you have this thing called stuttering. And stuttering is essentially that the system can choose not to run any step at all. So it can just stop. And this is an interesting to consider because imagine that, because if you don't have stuttering or if you don't have this termination, this assumes that things work all the time. Like that assumes that the producer and consumer are always available. But of course, working with systems, things break all the time. Now, if you have stuttering, then that means that something can stop. That means that maybe the consumer's down, maybe the producer's down. You can use it to mimic all sorts of different in your system. And there's also some other stuff you can do with eventual consistency, which is a bit later on, more advanced TLA plus stuff. But you can do this thing called, you can add a keyword fair. And what fair does is that if a property is enabled, or if a labeler is enabled, it'll. And so this is essentially sort of cheating, I guess. But if you run it again, you can back to it passes. But you can also see that the number of distinct states has returned back to the same number that it was before we enable a termination. So this isn't really, if you want to deal with termination, you have to make your models more, you have to handle that in different ways. So this is a cheap way to fix that. But so all of that being said, like I've talked about this, I imagine that most people might think, oh, this is kind of interesting, but how am I going to tell my boss I want to learn this thing that we're going to use? So how can, what can you learn about TLA Plus without having used TLA Plus? So, but also, like, this is actually used in production and used by used by Amazon. Amazon uses it they started writing their systems using TLA Plus. So there's an interesting article by Ron Pressler as well, who talks about what Amazon uses TLA Plus for. And then there's also, if you're not familiar with this, this is an asteroid, it's a comet, and it's comet Churyov-Gerasimenko. And this is a picture that was taken by the Rosetta spacecraft. So this is pretty cool, right? Like spacecrafts are pretty amazing. And so why do I bring this up, of course, because Eric Verhulst, who was the head of the group that developed this platform, said that TLA Plus abstraction helped a lot in coming to a much cleaner architecture. We witnessed firsthand the brainwashing done by years of C programming. One of the results was that the code size is about 10x less. So I want to highlight a few different things. One is much cleaner architecture. Like, this is a win, right? If you can, to paraphrase Thoreau, simplify. If it's a cleaner architecture, probably means it's a simpler architecture, probably means that there's less things to worry about, which means that there's less likely to have bugs and more likely for other people to work on it and these kind of things. And especially something, I don't write spacecraft software, so the stuff that, like, we can make mistakes and we can roll back and we can do these things, but something with, like, a spacecraft, you get one shot. So this is incredibly important. And I thought this was interesting as well. Witness firsthand the brainwashing done by years of C programming. I mean, we're all creatures of habit. We all do the same things. We get up, we do the same thing in the morning. I mean, I don't know the number of times I've written like authentication and authorization for a project, and a lot of it's done by muscle memory, or you copy code from other projects. So you just start getting into these ruts. You don't look at things fresh. But using TLA Plus or another model checker, you have to look at you have to develop the program in a different way. You have to take it bit by bit. You can't just copy and paste from another thing and think it'll work in this context. And because of the number of possible states, you can see that it's really impossible to verify that without it. So this yields new approaches and new solutions. And then finally, the last thing is, code size is about 10x less. If you don't have code, there's no bugs, right? And it's easier to iterate, right? A smaller code base is presumably a simpler code base, unless it's like a code golf code base. But the idea is that the less code means that you should be able to change things more frequently. And then there's a talk, Finding Bugs Without Running or Even Looking at Code, by Jay Parlar at Strangeloop this year, and it's about another model checker called Alloy. And it's a really good talk, definitely worth watching. And his conclusion is he doesn't expect people to use Alloy, but he expects that if you're going to take something away, it should be discussed beforehand. Draw diagrams, define a mental model, write stuff down. This is stuff that we've been told to do since the first time we read an outline in elementary school. And for some reason, we don't do that as much with software that we would do with another discipline, maybe because it's the assumption that you can just cut and paste and change things around. But it's really important to design things first. And it's something that I think done a bit better job at BR, and even with a distributed team, there's a lot more collaboration, which usually means that the end result is a simpler and more reliable execution. So, I was thinking, if there's something you can take away from TLA Plus, or something you can take away from this, and I said, maybe it is this idea of simplicity. And of course, Lamport phrased it better. The more complex a system is, the more important it is to make it as simple as possible. In complex systems, simplicity isn't achieved by coding tricks. It's achieved by rigorous thinking above the code level. So this, again, implies above the code level means anything between inception to writing the code. So writing things down, planning things better. And with TLA Plus, because everything has to be layered, especially as sort of a novice with TLA Plus, it's very difficult to take these mental models and to map them onto TLA Plus. So you have to sort of get rid of all the cruft. So if you can leave you with one thing to take away, it's keep things simple. Have constraints at work. Make the simplest thing that will work, that will satisfy your requirements, and that should help you have a much more reliable system. Thanks.